E-transcription feels like magic right up until it confidently writes the wrong word. You paste in an audio file, you wait a few seconds, and a wall of text appears, and most of the time it is remarkably close. Close enough that you stop checking every line. And then one day it transcribes a proper noun as something completely nonsensical, or it hears a technical term and types whatever sounds vaguely similar, and you only catch it because something felt off when you read it back. That is the moment when you realize you do not actually know what the model is doing. You have just been trusting a black box. So in this video, I want to open that box. I'm going to show you what is actually happening when a model turns audio into text, why the technology improved so fast, where it genuinely still fails, and the specific trick I use in my own setup that sidesteps a whole class of errors. If you work with transcription regularly, this will change how you think about it. This inicie how you think about it. What speech-to-text actually does. Let me start at the beginning. Most people assume the model is listening for the words the same way you are, matching sounds it hears to a dictionary. The reality is more interesting than that. What the model actually does is take a recording, usually a short chunk at a time, and convert the raw audio waveform into a grid of features. Those features are things like which frequencies are present at each moment, how they change over time, where energy spikes happen, things you would see on a spectrogram. The raw sound wave is not what the model reasons about at all. It gets converted into a structured representation first, and that representation is what the model actually reads. From there, the model does something clever. It does not just look at each tiny slice and guess a sound in isolation. It considers a whole window of audio at once, and it uses everything it knows about the probability of one word following another to figure out the most likely sequence of words that could have produced that pattern of features. This is why context matters so much. The model is not just transcribing what it hears one syllable at a time. It is making a prediction about the whole sentence using both the audio signal and everything it learned about how language works, why it got so good so fast. 10 years ago, automatic transcription was a novelty. It was interesting in a demo and mostly useless in practice. Today, it is accurate enough that millions of people trust it without thinking too hard. So what happened? The honest answer is that three things changed at roughly the same time, and they multiplied each other. First, the architecture changed. Older speech recognition systems were built on chains of separate modules that each did a narrow job. Modern systems use a single neural network end-to-end, trained to go directly from audio features to text. That removes a lot of the places where errors could compound. Second, training data exploded. Modern models trained on tens of thousands of hours of real human speech across many languages, accents, recording conditions, and topics. The more variety you train on, the more robust the model gets to conditions it has not seen before. Third, compute got cheap enough that you could actually train and run these models at scale. None of the three alone would have done it. All three landing together is what made it feel like a leap. What you are getting now when you use a modern transcription tool is the output of a model that has heard more hours of speech than you could listen to in several lifetimes. Where it reliably fails, names. Now here is the honest part that most explainer videos skip. This technology is genuinely good at general speech. It is not uniformly good at everything, and the places where it fails are predictable if you understand what it is doing. The first category is names. Proper nouns are hard for speech-to-text because the model predicts words based on probability, and rare or unusual words have low probability. A common English first name might appear millions of times in the training data. An unusual surname, a company name, a product name, a place name that is spelled nothing like it sounds, these appear rarely if at all. So when the model hears something it cannot confidently match to a high probability word, it reaches for the closest thing it knows. And the closest thing it knows by sound might be a completely different word. This is not a bug. It is a direct consequence of how probability-based prediction works. You can feed it a glossary in some tools, which genuinely helps, but without that hint, the model has no special knowledge that a rare name even exists. The frustrating part is that the error will often look plausible on first read. The model does not produce gibberish. It produces a real word that sounds like what it heard, and that word fits into the surrounding sentence just well enough that you read right past it, which is why names deserve a separate, deliberate check, not just a quick skim, where it reliably fails. Technical jargon. The second failure mode is technical jargon and domain-specific language. Same underlying reason. If the term is rare in general speech, its probability is low, and the model will mishear it. A security researcher talking about a tool by its proper name, a doctor using a drug name, a developer saying a library name out loud, all of these are high risk for an error. The worse the mismatch between the model's training data and the domain you are working in, the more errors you will see. This is actually a very useful heuristic. If what you are transcribing sounds like something from any mainstream podcast or news broadcast, the model will probably nail it. If it sounds like a specialist talking to other specialists about things the general public never discusses, expect more corrections. The scale of the mismatch matters too. A single unusual term in an otherwise ordinary conversation is a small risk. An entire recording of dense specialist language with new terms every few sentences is a much bigger one, and the errors will cluster in the exact places where accuracy matters most, where it reliably fails. Strong accents. The third failure mode is strong regional accents, and this one is more uncomfortable to talk about because the failure is uneven across groups of people. Models train on whatever speech data they can get. If a particular accent is underrepresented in the training set, the model will be less accurate for speakers of that accent. This is not a design choice, it is a data choice, and the industry has been improving on it, but it is still real. If you're transcribing speech from a speaker with an accent that falls outside the mainstream of where most training data comes from, you will see more errors. This is worth knowing because it tells you where to spend more time checking, and it is worth the industry knowing because it shapes how to build better training sets. If you are regularly transcribing a speaker with an accent the model struggles with, consider doing a short test first. Run a minute of audio and check the output carefully. That will tell you what you are dealing with before you commit to transcribing an hour of content and then finding the errors afterward, where it reliably fails. Overlapping speakers. The fourth failure mode is overlapping speech, and this is a hard problem. The way most models work, they assume one speaker at a time. They are not built to separate two voices mixed together in the same audio channel. When two people talk at the same time, even briefly, the model often drops one voice entirely, or it produces garbled output for the overlap region, or it assigns words from both speakers to one speaker, and the result is nonsense. Diarization tools exist that try to separate speakers before transcribing, and they help, but they add a step and they make their own mistakes. If your recording has interviews, panel discussions, or any moment where people talk over each other, treat those overlap regions with more skepticism than anything else. The best thing you can do during recording is give speakers a clear turn structure. A pause between speakers, even a short one, dramatically improves what the model can do. You cannot always control that, but when you can, it pays off downstream, where it reliably fails. Background noise. The fifth failure mode is background noise and low-quality audio. This one is the most straightforward. The model learned from clean speech. The further your audio gets from clean speech, the worse the predictions get. A fan running, keyboard noise, a loud room, audio that was recorded too quietly and then boosted, compression artifacts from a bad microphone. All of these degrade the audio signal before the model even starts. A modern model is quite resilient to mild noise. But there is a floor below which accuracy drops off sharply, and if your audio is already borderline, you should not trust the output without a careful check. Better audio in is almost always the single highest leverage improvement you can make to transcription accuracy. This is worth saying plainly because people often look for software fixes to an audio problem. Noise reduction tools exist and they help at the margins, but they are not a substitute for a better recording environment. If the mic is bad, if the room is loud, if the speaker is too far from the source, no amount of cleanup will fully recover what was lost. The trick I use in my own setup. Now here is the thing that changed how I think about transcription for my own work. Because everything on this channel is built from a written script, I almost never need the model to figure out what was said. I already know what was said. The script exists. What I actually need is timing. I need to know when in the audio each word happens so that captions appear at the right moment and stay in sync. And it turns out those are two very different problems. Predicting what words were said is hard. Matching a known sequence of words to the audio they came from is much easier. So instead of asking the model to transcribe freely, I give it the known script text and ask it to align that text to the audio. The model is only solving the timing problem, not the spelling problem. And because the words are already correct in the script, I never get errors on names, technical terms, or any of the other hard categories. The caption output is exactly what I wrote, placed where I said it. This is not a trick specific to video production. Anytime you have a transcript you trust and you just need the timing, feeding the text in, rather than asking for free transcription is the cleaner approach. It sidesteps the hardest part of the problem. Practical tips for anyone transcribing. With that in mind, here are the practical things I would tell anyone transcribing audio regularly. The first and most important is clean audio. Get the recording as clean as possible before it goes to the model. A decent microphone in a quiet room will help transcription accuracy more than any setting you can tweak afterward. The second is one speaker at a time, wherever you can manage it. If you are recording interviews, even a brief gap between responses makes a significant difference. The model performs much better when it does not have to handle overlap. The third tip is use a glossary if the tool supports it. Most serious transcription tools let you supply a list of proper nouns, technical terms, or names that should be spelled a certain way. This directly counteracts the low probability problem for rare words. It takes 5 minutes to build one for a project, and it will save you more time than that in corrections. The fourth tip is check anything that matters before you publish or share it. The model will sometimes be wrong in ways that are hard to spot on first read because the wrong word will often be phonetically similar to the right one. Read the important parts, do not just skim. And the fifth thing worth adding, pay more attention to checking the sections you already know are high risk. Names, jargon, accents, and noisy stretches. You do not need to audit everything with equal care. You need to audit the parts where the model is statistically most likely to have slipped. The honest bottom line on trust. So where does that leave us on the question of trusting AI transcription? The honest bottom line is this. It is genuinely very good at general speech in clean audio with one speaker, covering topics that appear commonly in mainstream speech data. Within those conditions, you can trust it for a first pass, and it will save you real time. Outside those conditions, specifically names, jargon, accents outside the training distribution, overlapping speakers, or noisy recordings, the error rate goes up and you need to check more carefully. The failure modes are not random. They are predictable, and once you know where they cluster, you can decide how much time to spend verifying based on where the risk actually sits. You do not need to read every word of every transcript. You need to read the parts where the model is statistically more likely to have made a mistake. That is a manageable amount of checking, and it gives you back most of the time savings while keeping the quality where it needs to be. The technology is a useful tool, not an infallible one. And the difference between those two things is exactly what I just walked you through. If you want more honest, no hype breakdowns of how this stuff actually works under the hood, subscribe and follow along. Thanks for watching, and I will see you in the next one.